Welcome back to Introduction to Computational Fluid Dynamics. I'm your professor, Steve Miller. Today we'll be talking about computational grid generation, with a particular emphasis on the algorithms of unstructured meshes. In the previous class, we looked at structured grids and their general description and generation techniques at the most basic level. We especially emphasize the advantages and disadvantages of structured grids. In particular, we looked at the metric transforms, which are the most important part of structured grids, so that the partial differential equations can be evaluated correctly. Then we talked about the connectivity of structured grids. Remember, the connectivity is implied based on the ordering and number of grid points in the index directions of I, j, and k. We briefly also talked about a solution using the boundary layer method. In this class, we'll talk about unstructured grid generation, and we're going to focus on the algorithms of how they're created. There's no so-called or simplistic metric transforms for the particular mesh as a whole, like as there is in the structured grid approach. Instead, with finite volume, one simply is evaluating fluxes across the surface of each particular volume. In finite element, they're transforming each particular element into a standard element, like a tetrahedral or triangle, with the same sides and angles. And the finite element method is applied uniformly to every one. So there's a type of transform for the finite element method, essentially. We will be talking about the Delaunay-Voronoi methods and the advancing front methods. These are two of the most popular ways to create the unstructured meshes that you see in computational fluid dynamics. We'll also talk about the combinations of the DVM and AFM methods, and we'll look at the surface and volume meshes as examples. We'll also look at a slightly less used approach, which is called QuadTree and OcTree. Then we'll talk about a few other miscellaneous things. Let's get started. Remember, for unstructured grids, we are looking, like structured grids also, to solve each equation in each grid point. Or, with a finite volume for a method, for example, we're solving for each equation within each volume. Elements and volumes, in terms of grid generation, are used interchangeably and are equivalent things. A finite element solver and a finite volume solver, which we'll discuss later, can use the same computational domains, which is a wonderful advantage. A finite difference space solver uses structured domains. Typically, if there's structure to the unstructured mesh, it might be able to be used in a structured solver. Finite element and finite volume solvers can most likely use structured grids. It's just a matter of accounting of how the connectivity and the type of grid and elements which are created for each particular solver. So there are some advantages there, and there could be crossover between the meshes and what solver they're used for. Remember, these can be directly applied with no particular transforms that are necessary. Volume and element methods are typically formulated and written in integral form, which most undergrad students are more familiar with. Today, we'll start talking about the two main methods, the DVM method and AFM method. Let us review just a few notable features of unstructured meshes. One in particular is that the number of cells surrounding a typical interior node, that is a node within the domain and not at the boundary of the mesh, is not necessarily constant. This means that a particular element or node may have multiple neighboring connectivity or neighboring elements, or perhaps volumes. This is unlike the structured meshes, which always have the same number of neighbors. The connections or connectivity is listed from point to point. Instead of using the so-called I, j, and k arrays, like in the structured approach, we now use a list of nodes, that is their x, y, and z location in space, and their connectivity between nodes. We'll see this in an example in a second. Typically, triangular and tetrahedral meshes are the most common for unstructured codes, though quadrilateral and hexahedral meshes can also be constructed. You can imagine I can take a structured mesh and simply write out the connectivity and use it in a structured solver. There are certain advantages and disadvantages for unstructured grids. First of all, the structured grid offers a major advantage in algorithm efficiency and implementation. It is most certainly the easiest algorithm to implement. Technology for CFD has been mostly originally developed for the finite difference approach and structured grids. You can read about this more, Bowyer, Morgan, and Pirro, 1990. They note that the structured grid offers choices of an appropriate solution method from among the large number of algorithms that are available. There are many, many more solution algorithms for structured meshes than there are unstructured meshes. This is one of the principal advantages of the structural approach. Of course, the unstructured approach has the biggest advantage of all in terms of creating the grids for complicated geometries. That is, if I have a very complicated boundary, for example, any type of part in engineering, complicated combustion chambers, the human lungs or heart, the basin of a river, it's very hard to have a structured overlapping mesh. I can have a single fluid domain or single mesh that represents very complicated geometry, as I'm simply triangulating the surface of these complicated shapes, which can then be connected to the volumetric part of the unstructured domain. Of course, the major disadvantages are that it is much more difficult algorithmically to create an unstructured mesh, and we'll look at those algorithms in a few minutes. Of course, the other major disadvantage of the unstructured approach is the increased use of computer memory. One should expect for the same problem to use more memory on a grid point basis and solver basis for an unstructured approach than an equivalent structured approach. Let's look at one example of an unstructured mesh and its connectivity. We'll look at a two-dimensional case. However, the three-dimensional case is the same, just using more nodes and connectivity for the same type of domain. Remember, in a three-dimensional mesh, you have surface meshes on the outside and boundaries. So even if you're in a three-dimensional domain, you still might have to create a two-dimensional mesh on the surface first. Let's look at the two-dimensional mesh now. Here in this figure, in the middle of the page, you can see one candidate two-dimensional mesh. The nodes are marked as black dots. The connectivity are the lines between each black dot. For example, on the left, we've listed the particular elements formed by the nodes and connectivity. For example, 1 is made up of nodes 9, 5, and 8. If we look at element 1 across, we see nodes 5, 8, and 9. Essentially, what this little table on the left represents is the connectivity list for the domain. The whole connectivity list is stored in a file along with the locations of each grid point. For example, in a file, the first line might be 3 Cartesian coordinates, which represent the first grid point. The second grid point would have another 3 Cartesian points, listing every node within the particular domain. After the nodal list, typically the connectivity list appears, and it just shows the number of elements, in this case from 1 to 14. So the first, the element number, and the second, third, and fourth represent simply that connectivity for each triangular within the mesh. You can imagine just by having more values of nodes in each row, you may be able to build up any arbitrary polyhedral. In 3 dimensions, for example, for a tetrahedral mesh, you would have 4 columns. You would have 4 nodes for each element in each row of the connectivity matrix to represent the unstructured domain. So storing these grids is very easy. It's simply a nodal list and the connectivity list. The major trick, of course, is how to come up with that in the first place, and that's what we'll be talking in a little bit. The first and perhaps most popular method is the so-called Delaunay-Voronoi methods. Let's look at one example on the right. Here we have a very complicated looking figure which represents the Delaunay Triangulation Voronoi polygon formation. What happens is initially there's some structured mesh which is overlaid the domain that would make up the unstructured mesh. In this case, it's simply a circle. Then a structured triangular mesh is created. This is just like the structured meshes we would talk about previously, but without the connectivity list. An implied connectivity list might be created. Then, of course, we can draw lines from the cell center of each triangular element to the center of each neighboring triangular element. This is the so-called Voronoi polygons, which I've listed in point 4 on the left. A collection of the Voronoi polygons is the so-called Dirichlet tessellation, named after the mathematician Dirichlet. He's also named after the boundary conditions which you learned in your differential equations course. In a sense, remember, each triangle for the Voronoi polygons formation is bisected within the points interior to each triangle. So you can see it's easy to create an arbitrary triangulation for any type of unstructured domain just by overlaying a structured set of triangles within it, which can easily be created with a numerical algorithm. Then the Voronoi triangulation can be created. Then at the boundaries, we simply truncate and create new grid points at locations where they cross the boundary. This is the most simple and straightforward type of method to create an unstructured domain. Let's look at some definitions so that we can understand it at a deeper level and maybe improve upon it. Let's look at the diagram on the right. We have a circle, and on the circle surface there are points A, B, C, D, and E, and F. Now if we place any 3 points on the circle, we can create triangles. The first set, A, B, and C, creates an equilateral triangle. The second set, D, E, F, creates a second triangle with unequal sides and unequal angles. You can see that if we place a point within the center of the circle, we'll define that as the so-called circumcenter. The circumcenter may or may not reside within the center of the particular triangular element. If we place any 3 points on the circle, either the circumcenter will be inside or outside the particular triangle we form. Based on this so-called circumcenter test, we either reject the triangle ABC or accept triangle ABC. For example, you might imagine that if the triangle ABC is an element in an unstructured grid compared to DEF, it might be superior because it has higher quality grid metrics. That is, has more properties of isometry compared to triangle DEF. Recall the grid statistics we discussed 2 class periods in the beginning of the module on grid generation. Now let's look at the so-called Delaunay Triangulation method. These algorithms result in, given a set of triangulation which is unique, it results in the most equilateral mesh for any given point set. And the grid generation points and triangulation are decoupled. These are major advantages computationally in terms of performance and its implementation. Now, it's not just as easy as creating the Delaunay triangulation, which we discussed graphically, the algorithm itself. It might also include diagonal swapping, that is the swapping and the connectivity between elements to improve quality of the metrics of the grid. It might include the so-called Bowyer insertion algorithm or sweep line algorithm. We're not going to talk about sweep line today, but we might talk about Bowyer insertion, which depends on, of course, the circumcenter test. There's certain advantages to this methodology also. There's a lack of uniqueness for any particular 4 points on the sphere or 3 points on the circle. There's a very complex logic for Delaunay triangulation for programming the boundaries. You can imagine that if we overlay grid points on a computational domain, it's very easy to create the interior points. But how these triangles are modified near the boundary becomes very complicated. And there's many numerical algorithms to change the grid points and connectivity at the boundary to create the best grid quality metrics at the boundary. There is a particular lack of uniqueness due to the numerical implementation of the technique. Technically, the method will always produce the same solution for simple cases, but in reality, when we put it in a numerical technique, with of course some if statements and logical statements in the code, things are no longer unique. There is a particular CFD error which is very high for high aspect ratio elongated cells. You can see that in the case between A, B, and C and D, E, F triangles on this particular previous slide. Now let's talk about the so-called Delaunay triangulation technique. We first, remember, start off with a set of points. We'll call those points P, and there's I number of points to N. So each point is at position index I in position X. Here X might be a vector. These are a set of the so-called points. From these points, we can create the triangulation. This might just be simple like a structured algorithm that initially creates it, or some other method like advancing front. Now, as the mesh grows, we can add more and more cells to the addition of the line segments, which are connected to each points in the triangulation. The boundary polygons, or the Voronoi polygons near the boundary, are those always that we define as the edge of the domain. There will always be a complete set of polygons that become the Voronoi set. Once again, let's explain this on the right. Each place where lines are connected might be a grid point of the Delaunay triangulation. Given any Delaunay triangulation, we can find the equivalent Voronoi polygons. Simply place grid points in between each triangle, and then move them to locations where the connectivity between each new grid point and each triangle becomes normal to the connectivity between the original Delaunay triangulation. You can see how this might be done, and the Voronoi polygons can be then seen as overlaid into Delaunay triangulation. You can also do this in 3 dimensions, except the connectivity between the Voronoi polygons will be going through faces of the triangles of the tetrahedrals in the Delaunay tetrahedral mesh. Now, many solvers, finite volume especially, can use either the Delaunay set, which would be a tetrahedral or triangular mesh, or the Voronoi polygons, which have, of course, a random number of faces depending on the particular mesh that we created. There is a superior way to create these Delaunay triangulated meshes, and it uses the circumcircle test, which of course is the simplest method to construct unstructured meshes and simplest to implement in a computer program. A number of triangles are laid out, and the circumcenter test is used to see if cells are valid, that is, if no other point falls in their particular circle defined by the triangle. That is the so-called Bowyer algorithm. On the right, there are 2 cells which are formed, for example, from this particular algorithm. One might start with an initial triangle over the whole domain, and in circumcircle tests and the Bowyer insertions, which use the circumcenter test, either fail or are correct. If they fail, then of course the triangular mesh is altered and more triangles are created or modified if the test fails. If the test is correct for the whole domain, then of course the computational domain creation approach stops and you have your final mesh. This is the most simple example of the failure of the Bowyer test and the correct test, meaning that the triangles are each containing their circular center. Think about programming this in 3 dimensions. That would be quite a challenge, and using lots of logical statements and of course some geometry. Let's look at another example to try and solidify these concepts. Here, A, the upper left figure, is some undesirable triangulation. Why? Because there's so-called some minimum or maximum criteria which is not satisfied. You can imagine that we take particular elements A, B, C, and A, C, D, and we would like to simply change the connectivity, but not change the nodal locations, because it might be a boundary, from A to C to D to B. That would retain the nodal list grid file, but change the connectivity list. It would be flipping to. How do we do this automatically for millions, if not hundreds of millions of grid points? Well, there should be an algorithm. And of course, this is the algorithm which we discussed, which is the Bowyer test. In the lower left, we would construct the outer circle, which contains A, B, C. It contains all the elements within the mesh. Then we could construct other circles, which are unique, which would be A, B, D, and B, C, D. You can see that these particular circles with an insertion in the circumcenter would satisfy the Bowyer test, and therefore that connectivity change would be correct. How this would happen in practice is we would go through cells and examine them numerically with grid quality metrics and select them as candidates to perform this test. Alternatively, you could perform this test on all elements and find that they all satisfy the criteria of the circumcenter test, and your mesh would be finalized. This is what's happening millions and millions of times a second within your computer when you're creating unstructured grids using these types of techniques. Let's look at an example of the Bowyer insertion algorithm. On the right, we have and I've shown this picture earlier, the Bowyer algorithm applied to the National Advisory Committee for Aeronautics, the NACA 0012 airfoil. Recall the 1-2 means that the airfoil is 12% thick, and the 00 means that it's symmetric. In this case, now we have a list of nodes and connectivity list between all nodes. That's the two types of tables to form it in 2 dimensions of a triangular mesh from the Bowyer insertion algorithm. Remember, it relies on the circle test, and there's a series of tree searches to determine the new connectivity and improve it. This is how the test is performed in most actual computational domain solvers. This will essentially refine the mesh by inserting more points and finding new connectivity. We can also use the algorithm to increase the number of grid points in regions that we're interested in. You can see in this case, they've tried to insert more and more grid points along the leading and trailing edge to find this tessellated mesh. It's the most basic example for a real-world application for like a wind tunnel test where we want a CFD mesh that you can find. Let's talk about the Bowyer insertion algorithm. Remember, first you need to generate a set of grid point locations. These might be uniformly structured. You can place the points randomly. They could be self-adjusting depending on some other algorithms. It could be dependent on the domain decompositions for multiple processors. It's really up to the user, and this is something which is a choice, of course, and you'll find these things through best practices. Today, of course, the initial grid point locations are simply estimated by the grid generation solver in practice. And then we create an initial triangulation. That's the so-called super triangulation that encloses the entire domain. That is, there'll be a giant rectangle over the entire domain and encloses it, and triangulations are made throughout it. Then a mesh point is inserted from a list of points in step 1, and we delete the first particular triangle going through a list that fails the circumcenter test. And this is the cell and point where a new point is inserted. Then a nearest neighbor search is found, and the nearest neighbor cell is deleted. The common faces between the first deleted cell must be removed, and the search proceeds through neighbors of these cells. Tree searches are made, that is a tree algorithm search, and it'll continue until completed list of deleted cells is compiled. There'll be a new connectivity list if this process is iterated, and newly inserted points with the boundary points of the cavity crafted by deleted cells. We will then add each of the new cells to the list of the valid triangles. We'll repeat this with starting at the third step of inserting a mesh point from a list of the current list of nodes until all the grid points generated through all these steps have been inserted, and you'll find the final mesh. This is the general Bowyer insertion algorithm. I've placed this in a table for you. One major issue, of course, with the Bowyer insertion algorithm is what happens near boundaries. We have to try and find boundaries which are coincident with the boundary of the vehicle, for instance, or a solid wall, or an inflow or outflow boundary condition. These are boundaries which we place. We'll talk about these more later in the class. For now, you should know that we try and place faces and nodes on the on the boundary of, say, a solid surface. That way we can enforce the boundary conditions that the flow is not moving through the wall. The Bowyer insertion algorithm itself often places nodes and connectivity that is going through a particular body. For example, at the trailing edge of the NACA 0012 airfoil, you might see an air that looks like this on the right. This is the trailing part of the airfoil, which is in black, or this grayish color. The white area is the fluid. Here, if we run this algorithm, we might come up with a case that looks like this, where we have one node in the fluid, two on the upper boundary or suction side of the airfoil, and one on the pressure side of the airfoil. One of the connectivities goes through the airfoil. It has satisfied all our tests of the algorithm, and so many logical statements must be placed within these algorithms to do checks to make sure that the connectivity is not violating the surfaces of vehicles, for example, especially where there's angles like at the end of a trailing edge of an airfoil. This can also happen in other locations or any regions where the part might be thin, for example, at the end of a nozzle lip. The Watson algorithm itself rejects elements, triangles in 2 dimensions for instance, from the set of all the triangles with non-empty circumdiscs. These can either be removed from the mesh or replaced with ones that pass the test. Let's now summarize the Watson algorithm. Initially, it'll be calculated through a various set of x and y coordinates of the boundary points surrounding all nodes to be inserted. It'll also calculate the circumradius of each x and y coordinate of the circumcircle. Next, in the second step, it'll introduce a new point within the field. It'll conduct a search of all current triangles to identify those circumdiscs containing a new point. For each such disk, there'll be an associated triangle flagged for removal. This union of all triangles, that is an insertion polygon, will be formed from them. Here, there'll be no previously inserted node which is contained in the interior of the polygon. Each boundary node of the polygon may be connected to the new node by a straight line lying entirely within the polygon. These new lines will form a new triangulation in the particular region, which can be shown to be a new Delaunay triangulation. So the Watson algorithm can be combined with the Delaunay algorithm. In the last step, we would repeat the introduction of a new point and go through the fourth step, which is the union of all triangles and insertion of polygons to form new Delaunay triangulations. This will happen over and over in an iterative approach until all the nodes which we wish will be inserted to find that triangulation, that is, his desirable characteristics that do not fail the circumcenter test. Let's look at one example of the Watson algorithm. Let us say our initial mesh is up here in the upper right. It has nodes 1, 2, 3, 4, 5, 6. And let us introduce a new point within our mesh. We'll say it's point number 7, which is in the triangle 2, 4, 6. Now each of these existing triangles in our mesh at some point has a particular circumdisk. And you'll see, if we find the circumdisk in the lower right figure, for example, you'll see that point 7 happens to lie within the triangles of 2, 3, 4, and 4, 5, 6, but not triangle 1, 2, 6. Well, that's good and bad. We will now flag triangles for removal that have circumdisks which do not contain the new point. Then we'll find an insertion polygon. The polygon remains after the flag triangles have been removed. For instance, now that we have these particular triangles formed, we would remove their internal connectivity and create connectivity from the newly inserted point, point 7, to 2, 3, 4, 5, 6, respectively. You can see that we've actually improved the quality of the original mesh before the insertion and change the connectivity to the new one. Look at the number of cells, however. We have increased the number of grid points by 1, and of course we've increased the number of elements or volumes from 3 to 5. This increases computational power, which is unfortunate, but on the other hand, we might be able to find a better solution that is more well posed for our solvers, especially in finite element and finite volume solvers. Note that the sides of each of the new triangle are straight lines from the ends of the points to the sides of the new point as shown in the final triangulation. We can repeat this process over and over and over to find a proper set of Delaunay triangulations that all satisfy the Watson algorithm, that is the circumcenter test. You might imagine now, how can this be applied in 3 dimensions for tetrahedral meshes? Well, this is much more complicated, of course, because instead of using a circular circumcenter test, you're using a spherical center test. In 3 dimensions, the problem becomes much more difficult for this reason. Let's look at an example for a circular domain. Initially, we might put out some nodes for a circle fluid dynamics problem. The final domain might be the outline like we see in E. We place points in locations. It could be arbitrary locations, but we'll try and spread them out evenly within that circle. Then we'll create the initial so-called convex hull or initial discretization of the mesh using one global triangle. You'll notice that initial triangle covers all the grid point candidates. Then we'll place a new point within that particular mesh using the Watson algorithm. We then can, of course, create a new connectivity list and boundaries from the Watson algorithm, which we just discussed. If we do this over and over again, eventually you'll get a mesh that looks like the one in the lower left. You'll repeat this process many times until you find a mesh which looks like the one in part D. You'll have a triangulation about the circular mesh and outer external triangles, which we would delete because they are outside the original fluid domain. And of course, we find our final Delaunay triangulations. without the so-called convex hull, and this would represent our final computational domain. So you can look and see graphically how these algorithms are implemented. They're implemented using, of course, the Delaunay Triangulation and the Watson algorithm to find triangular and tetrahedral meshes, which are one of the most popular meshes in finite element solvers, and of course, our favorite subject, computational fluid dynamics. Let's look at some more examples. In particular, I've pulled out two. Here in the upper row, we have a number of circles within a rectangle. These are all done in 2 dimensions, but could easily be done in 3. We've put 4 circles inside. We have our initial mesh. Then we have gone through the Watson insertion method, and we find our final Delaunay triangulation. This is definitely not well resolved enough for computational fluid dynamics. However, it's a good example. We would need many more points to resolve flows to these types of circles. We also do a meshing algorithm of a typical airfoil. Here's the initial mesh. Here's the second step, which would correspond to steps B, C, and D in the previous slide here. And then, of course, the third mesh in the lower right would be our final mesh after we've inserted our points, and they all satisfy our circumcenter test. Now, there's particular good things and bad things about the Bowyer algorithm. Remember that they both start with an initial grid surrounding the geometry, which we showed in the example here on slide 21. Then new points are added one at a time, and triangular circumdiscs containing the new points would be deleted. There are regions which will then be retriangulated by connecting points on the deleted triangles to the new point. The major difference between the Bowyer and Watson algorithm is that the Bowyer algorithm maintains the list of only the Voronoi polygons, and we can form the triangle list from the Voronoi diagram. The Watson algorithm, which we presented here, it'll choose to maintain the list of the triplets of no numbers, or quadruplets if you're in 3 dimensions, and they'll represent the completed triangles in a running list of circumcenter, and circumcenter radius of each formed triangle will be kept. Remember, we do not and have not discussed how the test and automatic algorithm of these points are generated. There's a whole field of mathematical algorithms that can be selected to do this. Some will be more optimal than others. These routines will, of course, not lead to unique meshes, which some people might find disturbing. That's because it's just because of the way these initial points are formed and what choices are made for the insertion points. These are completely up to the user and even might contain some randomness in the functions used to generate the initial point field. Now, we've talked about the triangulation meshes for volumes. There's a different approach which might be good for CFD and is often used to resolve turbulent boundary layers. This would be the equivalent method of clustering points near the boundary and doing structured grids with metrics. Here, we can go around the walls of the domain where there's solid surfaces and typically do advancing fronts. You can even find a full volume method with this approach. Here, I've drawn an outer part of the domain, inner part of the domain, and placed circles. Typically, we will discretize and put points along each of these particular domains. But right now, we'll just look at a mesh without an interior structure, like a cylinder in this case. It can be used for triangles, tetrahedrals, and quadrilaterals quite easily, and all these are implemented in most computational domain solvers. The advancing front method is called that just because of what it is. It is going around the boundaries, especially where you want to resolve the grid highly, to iteratively place grid points within the domain. Let's look at some examples so you can understand the advancing front algorithm. This is best done simply through an example and then placed down in paper as an algorithm in words. So initially in A, we might have a given domain. This might be given by this particular nodal list, 1, 2, 3, 4, 5, 6, 7, 8, with these particular coordinates. Let's look at one advancing front method example. Initially, we'll be given this domain. It's simply a four-sided domain in 2 dimensions. Next, we need to discretize the boundary of the domain. We talked about this before. Here, we choose to put 1 node at each corner and then 2 nodes along the connectivity between 2 walls. We do that just to have more grid points and to have better resolved flow. You'll note that unlike the previous approach, we do not place points within the domain. We only discretize the surface or lines of surfaces first. And we order the number of nodes advancing in a counterclockwise direction for this particular case. These node coordinates are shown here in the upper left. And we'll have nodes 1, 2, 3, 4, 5, and 6. These are the so-called background boundary nodes or initial fronts. So the initial front in the advancing method will define it as the connectivity of the original discretization from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 1. And we'll start advancing the front of 1 to 2 because, of course, it's the first element in the connectivity list. And we will simply choose to place a node in the domain at some distance away from the wall. Typically, this is a normal direction and chosen to make an element with good grid quality characteristics. For example, some distance away from the wall and making the angles of the element as equal as possible or close to each other as possible. And of course, if we want to resolve the boundary layer, we would place element, when we create it, as close to the wall as possible to resolve the boundary layer that we're interested in. Anyway, once we do that, then we create connectivity between 1 and 7 and 2 and 7, and we've defined our first element. What happens then? Well, we remove the advancing front from 1 to 2. Our new advancing front in this new algorithm would then be 1 to 7, 7 to 2, 2 to 3, etc., all the way to 6 and back to 1. We then advance the next front as in part D. We would advance the front from 2 to 3 and place point 8 in the volume. This is placed at maybe not the most optimal location, but we'll choose it there. You can imagine what happens next. We then create the new connectivity from 2 to 8 and 3 to 8, and remove the advancing front of 2 to 3. This still remains in the connectivity list because this is our second element we created. Then we look at, of course, the advancing front of 3 to 4. We can simply replace with node 8 a new connectivity from 4 to 8. Now we have our third element, and we advance our front from 4 to 5. And of course, we remove the advancing front from 3 to 4, and now we can create another new connectivity as in part F. We don't need to necessarily just keep creating connectivity as we go around the advancing front. We can just either keep adding nodes or create new connectivity. There'll be logical algorithms in the computer code using if statements or checks or geometry or all kinds of other types of things which are object of research so that the advancing front methods do not overlap. For example, from 5 to 6, I could actually place a new point, number 9, on the other side of 7. I would have overlapping elements. The algorithm is going to be checking that the advancing fronts do not overlap as they go around. Anyway, once we go around from 5 to 6, we will define that new connectivity, and we'll close our algorithm some 6 to 1 by joining connectivity of 6 to 7 and 1 to 7. And you might imagine that we have even bigger domains, and we might go around thousands, if not millions of times in a circle, creating these advancing fronts which come down and meet in the middle. To finish, you might also say, well, from H, I have some missing connectivity still, and I could advance and find the missing connectivity using 5 and 7, 7 to 8, and 8 to 5. You can see now that we're done, and the advancing front method is complete, and we have a mesh. We can then, if we wish, go back and try and improve the mesh by changing connectivity in the interior. We can use that with the so-called circumcenter test, which we discussed previously, if we desire, but it's not required. Then we can simply say we want to only perform the advancing method from the airfoil outward because we want more grid points around the airfoil. Well, in this case, we advance around the airfoil in the counterclockwise direction, adding points, and then reforming the connectivity as we advance outward. We would advance outward all the way to the outside mesh, and you would find something that looks like part F. Let's summarize in words the AFM algorithm. First, a background mesh is set up, and we define the boundaries of the domain, which we create grids. We then set up an initial front of these faces, and we march around these faces and deleting ones from the connectivity list. Then, of course, we need to find a procedure for deleting the worst faces. Typically, we try and find a best point, which is calculated. Then we determine if a point exists, then an already generated grid, and it should be used in lieu of a new point. You saw that in my original basic example, where, for example, we did not insert a third point. We simply created connectivity because it was in a cave type part of the grid. Then, of course, we determine where other elements should be formed with the selected points and if they should not cross any given faces. We would not want the advancing method to cross itself. That is, the front of the method should never overcome itself, like in a wave and a beach. Sometimes waves and beaches overcome themselves, while we wouldn't want the fronts of the advancing method to cross themselves either. As we go along, we're adding new elements and points and faces to their lists. So we're always modifying the nodal lists and the connectivity lists in memory. And we keep repeating this process from the fourth step, which involves deleting the next face for the advancing front method. And we repeat this until the whole mesh is complete. Then we can perform grid quality checks and modify the mesh and connectivity if required. You can also perform an advancing front method for quadrilaterals. Here's one particular example. We have cylinders in a domain. We have part of a cylinder. We have a wing with a flap, and we have a nominal aircraft. All these grids were generated with advancing front methods. The key difference between the triangulation and quadrilaterals in this case is that 2 points are inserted initially, and an additional point is inserted to create the next quad. Often these types of meshes are going to be mixed elements in that you have quads and triangular elements in them. This is not always the case. And so some mesh generation algorithms, like we might try in our code in our class, can create these types of quadrilateral meshes. They're much more difficult to create than the simple triangular mesh in terms of the algorithm. Now, there's many special considerations for these meshes, and it could be advantage in some case that a finite volume solver might prefer these types of meshes, especially for flows with high shear. We'll see these types of flows and examples later in the class. You can also do this, of course, in 3 dimensions and get a hex mesh, which is maybe mixed with prisms and pyramids and all kinds of other elements. These advancing front methods are very popular in CFD because, of course, they resolve the flow near the boundaries. Here's a list of a table of the comparison between the advancing front methods and the Delaunay-Voronoi methods. The major advantage, of course, of the advancing front methods is that you can resolve boundary layers and put high number of grid points in particular regions. The major advantage of the Delaunay-Voronoi methods, of course, is that they result in very optimal grid quality metrics for a particular case. Unfortunately, they do not have particular ways to resolve regions of high shear, which is critical in CFD. Now, typically, there's good things and bad things about both approach, but you'll have to decide which one's appropriate for your case. And it could be that you have to combine the two to use the advantages of both approaches and minimize the disadvantages of both approaches. Take a few minutes and read through the list. Now, I mentioned that we can try and take advantage of both approaches. These are the so-called combined mesh generation techniques. This is the combined DVM and advancing front method, AFM. So what we might do is create a background grid, which is generated from the advancing front method, and then use the DVM method for the predominant part of the domain outside the advancing fronts. Let's look at one example of the AVM DVFM approach. First, the exterior domain is created and it is discretized with grid points. Then the airfoil is created on the interior, and we put a number of grid points around the airfoil. We would say we would like to have quadrilateral elements around the airfoil because they're better for regions of high shear. We find that in high-speed aerodynamics, typically elements which are not triangular or tetrahedral are better in regions of high shear because of the solver issues of well-posedness, because of the numerical issues inherent in the solver, which we'll talk about later. Now, in this case, you can see that we've discretized the airfoil surface, and the user said, I would like to march out from the airfoil surface at some distance, say delta y. At each subsequent iteration around the airfoil surface, we increase delta y. So for example, near the airfoil surface, we have a very small delta y, and as we march out in an orthogonal direction, we have larger and larger delta y's. This surface might have 10 to 15 advancing fronts or layers. We might call these number of layers, and the number of steps is about 15, with initial step of about delta y of, say, 1 times 10 to the negative 8th meters. And each additional step might multiply the delta y from the previous step by, say, like 1.1. That is a 10% increase in spacing. These are settings that you can put in computational grid generation programs to tell the advancing front method how far to go into the field. They've also put out grid points within the field and gone around them to try and resolve some of the wake of the airfoil, especially in the region of the high shear where the two boundary layers meet. They advance out, and then we have, of course, a new surface, which would be represented in the fluid domain, which is only where the advancing front method. Between the outside and into the advancing front method and the exterior of the domain, we might use another approach like Delaunay Triangulation. In this case, they used a little bit different approach, which we'll talk about next, to fill in the interior of the grid between the advancing front method and the exterior of the domain where the air enters and leaves the computational grid. Let's look at a few examples. We've done all this in 2D, but all these algorithms can be extended to 3D. And this can just be simply extended through a graphical approach, if you will, and altering the algorithms to have the third dimension and using spherical checks instead of circular checks for the insertion methods. The surface meshes, of course, are formed from the two-dimensional approaches, but not in planes, but on curvilinear surfaces. So you can see in this example in the lower right, you can see one interior mesh, which might be on the wall for a symmetric boundary condition, and on the surface of this particular vehicle, you can see the vehicle has triangular elements, and the interior of the domain will be tetrahedrals. All these elements have to have closed form connectivity so that the mesh is so-called watertight, meaning that there are no holes or gaps or tears or two elements with missing connectivity. These things cannot always be seen graphically, and you'll have to have your computer program do these checks to look for the mesh and see if it's watertight. Some solvers, when they read computational domains, also do these checks. This is all done automatic for you, of course, with a computational grid package. There's other approaches. Two, which are a little less popular, are the so-called QuadTree and OcTree mesh generation algorithms. These use the concept of superposition and deformation. Simply, you construct a structured mesh in 2 dimensions or 3 dimensions and remove elements which are not in the interior of the domain. It's most easily understood graphically like the other algorithms. So for example, we want to create a computational domain within this happy little hungry Pac-Man character, or half moon. We first place a large box around it to encompass the whole domain. Next, we create a structured computational grid through it, and then, of course, almost ignore the connectivity. Next, we identify all the interior nodes and connectivity and any connectivity which crosses the domain. We then get rid of the domain outside of the area where we want to discretize the mesh. What's interesting is that you can go in and do further refinements in each cell. For example, the original cells that cross the line of the domain, the outer boundary that we're interested in resolving, might be further decomposed into smaller and smaller meshes. You can imagine this is a little bit like a fractal approach, where we take each cell where we want to have more grid points, perhaps it's on the boundary or interior, and keep dividing it and dividing it. Let's summarize what we discussed today in computational grid generation for unstructured grids. We talked about the connectivity list and the grid point locations. The challenge is, of course, is to find these values. Where should the grid points be and what should the connectivity be to have a high quality grid, using, of course, the least number of grid points to resolve the flow to conserve computational power, but enough to be able to find a high quality solution. We talked about 2 major techniques, the DVM technique and the AFM technique. Remember this Delaunay-Voronoi method and advancing front method. The process is simple. We clean up the surfaces of a CAD model, for instance. That's the edges of the computational domain of the surface. We discretize particular lines that make up that surface mesh with grid points. Then we create surface grids on all the surfaces of the vehicle or part or object we're finding the flow around. Then from those surface grids, which should be watertight, we would create a volume grid which is watertight. The surface grids and volume grids can use all the same techniques, DVM or AFM or others, and we can mix them to our advantage. And so through time, as a user, you'll decide which ones are optimal for you. This is a very complicated and active field of research, and the software, high-quality software, to create these grids is often very expensive. There is some open source software that's free to learn from too. Anyway, you can try creating your own grids through, say, programming them, which is a wonderful exercise so you can still really understand the grids. You can try a few by hand in the most simple techniques to understand the basic concepts like we will do in our homework. And you can try these grids with some computational software packages. Here's an even more complicated case where structured grids are certainly not appropriate. It is an early form of the Ares or Space Launch System of NASA. This is a NASA work published through NASA Technical Report Server. So here's the diagram and shown surface meshes. This is essentially a CFD simulation for the launch abort system. The crew members would sit, of course, in the capsule shown on the right. On takeoff, this would be the top of the vehicle and this capsule bottom. And the bottom of the capsule would, of course, contain the heat shield for re-entry. If there's a problem on launch, these abort motors fire and it removes the capsule from the launch system and carries the astronauts, for instance, to safety. On the right, you see one particular plane cut out from the final three-dimensional mesh to show the tetrahedral mesh itself. This is probably created with a Delaunay advancing front type method. You can see that in this particular close-up of the strut structure around the launch abort motors. Here's the nozzles for the launch abort motors. The surface grids are colored in yellow and red and purple and other colors around these struts and members. Here is, of course, the top of the capsule you see right here. Now you can see the interior grid. These are all these tetrahedrals. These are all in 3 dimensions that wrap around the whole volume of the aircraft. We've just cut them out of the mesh so you can see the interior. If you just look at this mesh from the outside without removing cells for visualization only, which we'll see in the visualization part of the class, then you can make these types of plots from 3D too. It's a lot of fun, so you can inspect your mesh quality. If you do this, then you can see the surface grid. For example, all this surface grid is the colors. Then you can, of course, see the advancing front method near the wall of the vehicle. Remember, the advancing front method worked in 3D across all surfaces shown here. We're only examining the advancing front method in 3 dimensions with these particular cuts of the plane for visualization. You can imagine how much easier it is to create a mesh like this using advanced mesh generation software compared to doing a structured mesh where we have to wrap it all around and create many overlapping blocks. Another quick example might be a mesh for the human lungs. In our next class, we're going to change subjects. We're going to examine the basics of fluid dynamics. Then we will talk about how these fluid dynamics basics are represented by the so-called integral equations. We'll also review again the Navier-Stokes equations and an alternative form often used in CFD today and is a growing field, the Boltzmann equation. Thank you very much for your time today. I'm your professor, Steve Miller.